Hi, my name is Victoria Vlazos, and I'm going to work on problem 19.52. So we're given a network that looks like this. And we have 4 resistors. These given values, we're told that the EMF equals 57 volts, and this R equals 3.25 ohms. So what we're asked to do is first compute the equivalent resistance of the network in the figure, and we're told that the battery has negligible internal resistance, so we're setting little r to 0. Okay, so part A, compute the equivalent resistance. So first we need to identify if we have resistors in parallel or in series, and in this situation we have both. We have R1 here and R2 in parallel, we have R3 and R4 in parallel, and then both of these resistors parallel resistors are in series with each other. So that's going to take a little work to figure out the equivalent resistance. That's basically asking for the net resistance on all 4 of them together. We know that R1 and R2 are in parallel. Just write it out so we have it clear, and we'll call that R parallel 1. R3 and R4 are also in parallel with each other. That'll be RP2. And then we know that R1 and 2 with R3 and 4 are in series. So then what we need to do is add up all the values for the resistance. In order to do so, first we do the parallel resistors. You do the math here, and that comes to 2.11 ohms. And then for the resistors that are in series, we just add those up. And that comes to 5.11 ohms for, we can call the series R equivalent as well. Now on to the remainder of the problem that asks us to find the current in each of the resistors. So this one gets a little complicated because in order to find the current through each resistor, we first need to find the current for the entire circuit. So in order to do so, we use this equation, I equals epsilon over R plus internal resistance. We're told that the internal resistance is negligible, so that just equals 0. And this resistance is going to be the equivalent resistance. That's 57 volts. And the equivalent we figured out was 5.11 ohms. Do the math there, that comes to 11.15 amperes. And that's for the current in the entire circuit. So now we need to find the potential difference across each individual resistor. And that is using the equation V equals R times I. So then for V1, that's through the parallel connection of R1 and R2. So we're going to use the values that we found of R parallel 1 times this I value that we just found, 11.15 amperes, 23.53, and that's going to be in volts. And then for V2, that's going to be the parallel resistor value that we found earlier, R parallel 2, times the current for the entire circuit, comes to 33.45 volts. And then we're going to use those values to calculate the individual currents through each resistor. So for the first resistor, we'll call that I1. That's going to be equal to the voltage over the resistance of resistor 1, and that's going to be 23.53 volts divided by the given values from the problem, 7.24 amperes, I should say. For the second one, we're going to use a V1 again because the resistor 2 is part of that first parallel series, or parallel connection, I should say. And we're going to take the value for R2, and that is 23.53 volts divided by R2, which was 6.00 ohms. That equals 3.93 amperes. The current for the third resistor, we're going to use the value of V2 for this one, and the third resistor is R3. Pretty much just plugging in here. That's 2.79 amperes. And then the current for the fourth resistor, again V2 over R4, the last resistor, gives us 8.36 amperes. So there you have it. We figured out the equivalent resistance for the entire network, as well as the individual currents for each resistor.